this time again just via Zoom. So our lecturer today is Peter Muršič, and he will talk about, as you could see, strong cliques in diamond-free graphs. So Peter, please, and I guess if participants will have any questions, they could just ask during your talk, and there will be also time for questions at the end. So Peter, go ahead.
Hello, my name is Peter Muršič. I'm going to talk about strong cliques in diamond-free graphs. This is a joint work with Nina Chiarelli and Martin Milanic, which are also from this university, as well as Bernice Martinez Barona, which was a student who was visiting here for like a semester earlier last year, as well as Jerome Monod, who sadly passed away about a year ago. So first of all, let's start with some definitions. A diamond is a K4 minus an edge. So this is the graph here. Next, F-free graphs. So this is the family of graphs that do not contain an induced subgraph isomorphic to F. So for example, here we see there is a diamond, as well as there is a copy here and here. So this is not diamond-free. This one, for example, is diamond-free because all of those diamonds were removed with this removal of this edge. So this is an example of a diamond-free. And this is also diamond-free. Now, notice we say induced subgraph. Now, even though the diamond is a subgraph of K4, it's not an induced subgraph. By induced, we mean that we only remove vertices. So an induced subgraph is obtained from the graph by just removing some vertices and all edges that were incident to those vertices. However, existing edges between vertices that were not removed remain. So therefore, we cannot remove an edge in here. So therefore, this K4 is diamond-free. Next up, we have the notion of the clique. So clique in G is a set of pairwise adjacent vertices. For example, the red ones form a clique, as well as any of these form a clique. So this or the triangle up here or this triangle. Also, it's not necessarily maximal, so each edge is also a clique. Also, a single vertex is a clique as well. Also, omega G, this is the clique number, which is the maximum size of a clique in G. So in this case, the maximum size is 3. Next, we have a notion of a stable set. It's very similar to a clique, but stable set is also known as an independent set, is a set of pairwise non-adjacent vertices, which is a clique in the complement of G. So, for example, these 3 vertices are not adjacent to each other pairwise, and therefore these are stable set. And also, this is the maximum size independent set, stable set, so 3. So this alpha G is the maximum size of the stable set, which in this case is also 3. And also there's the notion of maximality versus maximum versus maximal. So any maximum is necessarily also maximal. So maximum means largest size. So in this case, maximum stable set was that one of size 3. However, this one, the marked one, is maximal as well, but it's not maximum. Maximal means it's not contained in a larger clique or stable set. So if we were to add another vertex to this pair, we would break the property of stability. So any of these vertices added would not be a stable set anymore. Okay, some more definitions. A strong clique is a clique that intersects all maximal stable sets. For example, this is a strong clique. Now, what do the maximal stable sets in this graph look like? Well, we've seen one when we take these edges at the very end, these free edges, and there's also the free pairs when we take one vertex here and one on the opposite side. So this plus the rotation. So for example, these two and these two. And we see that this clique intersects all, hence is strong. Similarly, we have a notion of a strong stable set. So this is a stable set that intersects all maximal cliques. The maximal cliques in these graphs are four of these triangles. And we can see that this pair, this independent set, stable set, intersects all of them. And here's also an example of a non-strong clique. This clique is not strong because it does not intersect this stable set. So these two do not intersect, hence neither of them is strong. Next, we have this notion of a CIS graph. So CIS graphs are graphs in which every maximal clique intersects every maximal stable set, or equivalently, every maximal clique is strong, or equivalently, every maximal stable set is strong. So for example, this thing, this sample graph has a pair of a stable set and clique that do not intersect. Therefore, this is not CIS. And here are some examples of CIS graphs. So first we have C4, as well as all complete bipattern graphs satisfy this rule. Remember, we have a two maximal independent set. One is, let's say, by this picture on the left, one is on the right. And all cliques are simply edges, and each edge goes from left to right, hence they all intersect. So that's why the complete bipartite graphs are CIS. And this is not necessarily, you don't necessarily need the same size on each side. So it could be different size. Next, we have, well, cliques, for example. So Kn, because there's only one maximal clique that spans all vertices, and all independent sets are simply just simple vertex. So they all intersect. Next, we have the diamond. The idea is here, there is only two maximal cliques. And why do they intersect all maximal stable sets? Well, for example, take this clique, and if these two vertices are not in the maximal stable set, then this one must be. So that's the argument that similarly holds also in this case, for example. Say, take any of these maximal cliques. You can also take this edge. If you do not take this vertex, for example, for this edge, to be part of your maximal stable set, then you can take this vertex. So therefore, this one intersects all of them. And therefore, this is CIS. And then we also get this type of graph. I'll explain later how we get it, but imagine we have a square grid, and each row and each column is also a clique. So if you were to enlarge this, we would need to add some extra edges to make all of this is a clique. And of course, maximal cliques are simply rows and columns. And maximal independent sets are basically pick a vertex, remove all of these because they cannot be in there. Then we get a one smaller size graph of the same type, and then pick another vertex, and you can reduce this, and you will see what we end up is an independent set that has this property that has as many vertices as there are rows, and each vertex it has its unique column and unique row. So therefore, we can also interpret from that all the independent sets and maximal cliques and maximal stable sets intersect. Okay. Next, our focus. So our focus is structural and algorithmic questions on strong cliques and stable sets in the class of diamond-free graphs. So here is some motivation. Why is this interesting? So strong cliques and stable sets are useful in the study of perfect graphs. Perfect graphs is a family of graphs where the chromatic number is the same as the maximum size clique. Also, strong cliques and stable set give rise to many algorithmic open questions. In particular, no good characterization or recognition algorithm for CIF graphs is known. And the class of diamond-free graphs is interesting because it is a generalization of bicutter graphs and triangle-free graphs in which maximal cliques are of size at most 2. And because we have this very nice property that every edge in a diamond-free graph is in a unique maximal clique. Okay, so now we have this table, and on the left side are all the graphs on 4 vertices, all the non-isomorphic graphs on 4 vertices, with the exception of P4, which is self-complementary. We have 13 different non-isomorphic graphs, and I listed them in pairs by complement. Now, why is that? Well, we're interested to know if the class of F-free graphs is CIS. Well, the thing about CIS graphs is if a graph is CIS, then its complement is also CIS. So if we can answer this question for F efficiently, then we can also answer this question for F complement free graphs efficiently. That's why they're in pairs. And here are some of the known results on the class of F-free graphs where F is these 4 vertex graphs. So which F-free graphs are CIS? In the case of P4 free graphs, all of them are CIS. So if we are given a P4 free graphs and the question is this CIS? Yes, it is. Second is a C4, which C4 free graphs are CIS? Well, they are CIS if and only if they are clique simplicial. We will now discuss what this clique simplicial term means, and then we will return back to this table. Okay, so you're probably familiar with what a simplicial vertex is. A simplicial vertex is a vertex whose neighborhood is a clique. So for example, the red one, the neighborhood is this, and this forms a clique. So similarly, this vertex is also simplicial, this vertex is also simplicial, and none of these are simplicial. Next, a simplicial clique is simply the simplicial vertex along with its neighborhood, like this. And a clique simplicial graph is a graph in which every maximal clique is simplicial. So for example, here we see this clique is simplicial because we have this vertex. This clique is also simplicial because of this simplicial vertex. This one is also simplicial because of this one. However, we have another clique in the middle, and this one is not simplicial. So this would not be a clique simplicial graph. However, this one is. So we have this simplicial vertices, this, and the last clique is now these two cliques. This clique is removed, and this one is transformed into a single edge. And this one is also simplicial because we have a leaf. So we're turning back to this. So C4 free graphs are CIS if and only they are clique simplicial. And we can check this in O of n to the 5th time, and this algorithm relies on a second property that we have at most O of n square maximal cliques. Then for K4 free graphs, the key idea is that each clique is of size at most 3. And the algorithm is essentially just brute force. Take all six vertex subsets and just check. Do these three form a clique, and do the other three form an independent set that is also connected to each vertex of the clique? If that is always, if we find that, then we can say, is it CIS? It is CIS if, of course, this does not happen ever. If it does happen, then it is not CIS. And similarly, this also works if we go for Kn. Of course, the testing coefficient does go up to 2 to the n times. Well, I think I used n twice, so it just goes up by 2 each time we add an extra vertex to our K complete graph. Okay, next is this graph here is the PO, and PO free graphs are CIS if and only if they are P4 free, and we can check if they're P4 free in linear time. And next we have the CLO, which is this graph here, and as shown by Alcon, Gutierrez, and Milanich in 2019. This can be checked in linear time as well. However, the diamond-free case is open, or at least was open. Which brings us to our results. So let G be a connected diamond-free graph. Then G is CIS if and only G is either clique simplicial, G is isomorphic to the complete bipetide graph, K and N, or some M or N at least 2, or G is isomorphic to the line graph of K and N for some N at least 3. Okay, we know what clique simplicial means. We have discussed it. Let's recall each clique has a simplicial vertex. Complete bipetide graphs we know. Line graphs I haven't discussed, but what you do is for each edge here. So if you take, it's the same graph. So for each edge here, you create a vertex here. So 9 edges here means 9 vertices here. And you connect the 2 vertices if the corresponding edges intersect. So for example, 1, 2, 3, they intersect here. It means they form a clique here. For example, this one, but it's very symmetric, so it could be another one as well. And of course, here for line graph, it's important that this is a square, while it's not important here for the bipetide graphs. It's not important that they have the same number of vertices on each side. Okay, so now we discuss the consequence of the previous theorem. So there is a linear time algorithm that determines whether a given diamond-free graph G is CIS. Now, the bottleneck to achieve linearity is the recognition of the clique simplicial property. Now, instead of checking this property directly, we check whether the graph is at simplicial, that is, every edge is contained in a simplicial clique. The 2 properties are equivalent in the case of diamond-free graphs, where every edge is a unique maximal clique. So again, at simplicial means every edge is contained in a simplicial clique. For example, this is at simplicial. So this edge is part of this simplicial clique. This edge is part of this simplicial clique. And you can make this argument for every edge. However, this is not a clique simplicial graph, as we said before, because this clique is not simplicial. And it's also one of the small counterexamples that these two properties are the same in the case of all graphs. However, when restricted to diamond-free graphs, we said we have this property that every edge is a unique maximal clique, and in that case, these two properties are the same. Okay, so now we can fill this out. So the last case of the diamond-free case is now solved. So the diamond-free graphs are CIS if and only they are clique simplicial, KMN, or the line graph of KNN. And this can be done in linear time. Okay, so now we have this nice theorem that for every F3 graphs, where F is on at most 4 vertices, we can check in polynomial time whether this graph is CIS. Another result is the improved Erdős-Hajnal property. So a graph class G is said to satisfy the Erdős-Hajnal property if there exists some epsilon greater than 0, such that every graph G in this class of graphs G has either a clique or a stable set of size at least the number of vertices to the power epsilon. The Erdős-Hajnal conjecture says that for every graph F, the class of F3 graphs has the Erdős-Hajnal property. Again, this is a conjecture. We do not know that in general, but we do know for the class of diamond-free graphs. And a simple argument in the case of diamond-free graphs shows that this inequality holds with epsilon equals 1/3. And what we've done is improve this to 1/2. So let G be a diamond-free CIS graph. Then the stability number times the dependence number is at least, or well, the other way around. The stability, the stability times the clique number is at least the number of vertices. Consequently, G has either a clique or a stable set of size at least the number of vertices to the power 1/2. And this is where this 1/2 as epsilon comes from. Next, we will look at some other problems. So these are the, it turns out that not all problems are easy in the class of diamond-free graphs, and these will be the hard ones. So the first problem is strong clique. Given a clique C in a graph G, is C strong? Then we have the strong clique existence. Given a graph G, does G have a strong clique? The next question is the strong clique vertex cover. Given a graph G, is every vertex containing a strong clique? The strong clique partition problem asks whether given a graph G and the partition of its vertex set into cliques, is every clique in a partition strong? And the strong clique partition existence asks, given a graph G, can its vertex set be partitioned into strong cliques? Now, all of these problems are hard for general graphs. Namely, strong clique and strong clique partition are QMP complete. Strong clique vertex cover and strong clique partition existence are QMP hard. And strong clique's existence is NP hard. And some of these were also shown by our Dean, Fidurovic, Milanic, and Rees in recently, and some quite a bit ago. However, the diamond-free case was open, so the question is, do these problems become easier in the case of diamond-free graphs? And the answer is not really. They are still hard. Namely, the first four problems are QMP complete, and the strong clique partition existence is QMP hard. The proof idea for reductions. So we will show one of these proofs, not all of them, because we probably, well, I didn't prepare more, but we probably do have time. Now, the main idea is a reduction from free colorability in the class of graph G, where this class is the class of all triangle-free graphs with at least 5 vertices and minimum degree at least 3. Now, first, the free colorability. Of course, ask, can we color vertices with 3 different colors such that the same color vertices are independent sets, right? And the free colorability in the class G, the more restricted version, is also NP complete. And this is our initial starting point. First, we'll construct G prime from G. So we are given some graph G, which will be for free colorability. Of course, we'll forget for that in a second. So how do we construct G prime from G? So first take any graph G, forget about these S's for now. You take the graph and you make 3 copies, 1, 2, and 3. So these are the 3 copies of G. And we also add another clique, the size of the number of vertices of G. And then we connect all these vertices in the 3 copies of the same vertex plus 1 vertex of the clique. We further connect this into a clique. So this is how we construct G prime from G. Now, we said that G is part of this class of triangle-free graphs with at least 5 vertices and minimum degree of at least 3. So first of all, this triangle-free graph, since G is triangle-free, it implies that G prime is diamond-free. Next, we will show only a part of the proof, namely that G is not free colorable if and only if C is a strong clique in G prime. C is this clique, this big clique we added. So G is not free colorable if and only if C is a strong clique in G prime. Or equivalently, G is free colorable if and only if C is not a strong clique in G prime. So how does this proof go? So we will show the negation. So suppose G is free colorable. Suppose G is free colorable. Then we have color classes S1, S2, S3. Again, these are independent sets. So S1 is an independent set, S2 is an independent set, and S3 is an independent set. Now take this S prime, S1 prime, S2 prime, S3 prime. Well, what are these? These are simply the copies of G in the respected components. So S1 is the color 1 class in the first copy, S2 is the color 2 class in the second copy, and S3 is the color class in the third copy. Now, what do we know? Since these are independent, these are still independent. However, we also know that there are no edges between these, right? There are only edges in the same level and the edges from G here. So there are no such edges that connect, for example, S2 and S3, and the same holds for any other 2 pair. So we can deduce that this gray colored union is also an independent set. And since we have 1 vertex from each level, we can infer that we have exactly 1 vertex in each level. Hence, all of this, each vertex in this clique C is connected to some vertex, is adjacent to some vertex in our independent set. We can conclude that we cannot add any more vertices to this independent set. So this independent set is maximal. And this clique C is also maximal clique. So we have a maximal independent set, a maximal clique, and they do not intersect. we can then conclude that this clique C is not strong. Okay, for the reverse, we start with the assumption that C is not strong, and we want to get a free coloring of G. So assume C is not strong. What happens then? Then there must exist some maximal independent set that is disjoint from C. Okay. Now, first, since it is independent set, we can infer there is at most one vertex from this independent set in each of these rows or levels. There is at most one. Next, we can infer there is exactly one vertex in each of these rows. Why? Well, first of all, it's disjoint from C, so it lives in these free copies of G. So suppose there was one of these rows where we would not take the vertex. Suppose we didn't take a vertex from this row. Well, then we can take this vertex. So if our independent set is here, well, then it's not maximal because we could take this vertex. So if we infer that in our independent set that is just disjoint from C, there is exactly one vertex in each of these rows. Okay, so once we have that, then we simply say, okay, let S1 be the vertices that are in the first copy, let S2 be the vertices that are in the second copy, and let S3 be the vertices that are in the third copy. Okay, and now if we project this back to G, well, we know there is exactly one vertex from each row, so this uniquely induces a color in the original graph based on which copy of G this is in. And since the whole thing was independent set, which means also these local smaller copies are also independent. So hence this is a coloring for G. Okay, so again, we proved G is not free colorable if and only if C is a strong clique in G prime, and this is where the MP hardness comes from. Co-MP hardness, sorry. Okay. Now let's look at, I'm at the end, I'm a bit short. We probably have 10 more minutes to talk about stuff, but let's look at an overview of the results we've done. So first, for these 5 problems that we just talked about, we've shown that they still remain hard in the diamond free case. The CIS recognition and the strong clique edge cover, these are polynomial in the diamond free case, and they are still open for general graphs, and they are open for quite a few years now. So we can see earliest is 1995 for the CIS recognition and 2003 for the strong clique edge cover. Okay, so that's it for the talk. Do you have any questions?
Okay, thank you, first of all, Peter. And yes, of course, any questions, suggestions?
This sysgraph business, it has a feel of some of the intersection problems people look at in other places. Is there some kind of Erdős-Hajnal type analogy, maybe for looking for the largest cis subgraph or induced subgraph?
I'm not sure what that is. I'm sorry.
For, well, people are often interested in looking at the largest intersecting system or largest cross intersecting system. So here you have a cross-intersecting system. So you've got these maximal cliques and maximal independent sets, and you're interested in requiring those to intersect. So this is the kind of problem people look at in extremal set theory, where the extremal set theory, and I mean extremal whatever theory, where the question is, the typical question is along the lines of what is the largest cross-intersecting system, or sometimes what is the structure of a largest cross-intersecting system. So the I mentioned Erdős-Hajnal, that characterizes the largest intersecting family of sets. That's sort of the grandparent result for all this sort of stuff.
Again, I do not know how to answer that. I'm not familiar with this.
Okay, any other questions?
Maybe I also should, I didn't mention this, but CIS simply stands cliques intersecting stable sets. Be easier to remember.
Okay, if there are no further questions, I will thank Peter once again, also in the name of the other participants, and hope to see you next week again at our seminar, again just via Zoom, of course. Stay healthy and see you next week.